So unit 2, the atom. Now we're finally kind of getting into some real more the what makes chemistry what it is, and that is first off, what separates us from a lot of different things is the atom. The concept of the atom is nothing new. The concept of the atom started by Democritus, and just like almost any and all things that we study in school, they all started with or at least has their roots in ancient Greece. So we're no different, and chemistry is no different. And why is that? Well, these people, they sat around and did a lot of thinking. And when you're going to sit around and do a lot of thinking, you're going to come up with some ideas that are going to be amazing. Democritus, one of the first people to kind of really bring it into the forefront. And that's what we're going to look at is what he did, and he coined the term atomos. Now, one of the things that for my class that you'll find is I will have some dates and some and the names of these people, and it's kind of more so that you kind of know where they fit with respect to the others. So when it comes down to this, it's what did Democritus do? He coined the term atomos. Talked about this idea of these indivisible particles that we can't see and we can't break them down any further. And because Democritus had a lot of clout, a lot of people were like, oh, he's super smart. They believed him. However, if you want to make yourself in ancient Greece seem smarter, or you disprove using reasoning and logic, your teachers or your predecessors, Aristotle and Plato, disagreed with this. Aristotle and Plato said that matter could be divided an infinite amount of times. And that is not a new thing. It's not. It holds very true for very, very long times. And when we think about it, it's like, from just a conceptual point of view, and that's how you have to do this, because you got to remember, they don't in ancient Greece, they don't have the technology that we do. So what they have to deal with is like, you say you take this big mountain, and a rock falls from it, and it lands onto the ground. Comes down the mountain, rolls down the mountain. And you can take that rock, that boulder, and break it down until it's smaller rocks. And ultimately, it's still, and they reasoned it that rock, those smaller rocks, just came from the mountain that it fell from. And you can take those smaller rocks and keep crushing them down and down and down until they're just grains of sand. Now that sand is just crushed rock. Now that crushed rock came from the mountain. So really the sand is just smaller pieces of the mountain. And we could keep crushing and crushing and crushing and crushing and crushing the sand into a very fine dust. And that dust just came from the sand, which came from the rock, which came from the mountain. So ultimately this dust is just another piece of the mountain. Just a really small piece of it. And their reasoning was, if you could crush that dust farther and farther and farther down, that it would still be just part of the mountain. And to the common folk, that makes a lot of sense, because that's something they can visually see. And that's what allowed them to say, yes, that makes sense. You guys are geniuses. And in some ways they are. However, they're not telling us the whole story. And Democritus actually had some ideas that allowed that other people were like, no, that's kind of smart. But Aristotle and Plato's idea was very conceptual. It makes, to me, a lot of sense that a person would think, oh, it's just a smaller piece of the whatever it was, and we can just keep breaking it down. And that's why it held for so long. And now, there were people that thought of that just didn't make sense. There were some things that, like, then okay, if everything's a piece of this big mountain, where do we get these other elements from? Where do we get these other metals from? And how does that work? It doesn't explain things. And they want that explanation of how did that metal come to be? And nobody could explain it using that method. And so they had to come up with some other ideas, and then you would get this idea of alchemy brought in, and that these other metals, you can turn different things from different things, and that couldn't happen if you're following Aristotle and Plato. It could happen if there's these things called atoms. Now, John Dalton, a lot of times they reference him in books as an English school teacher. John Dalton wasn't a teacher of English. He taught science. It's just he taught in England, and therefore he's English. Okay? And John Dalton was able to do what a lot of some of the scientists that we have do, is that we have a lot of these people and these different ideas all over the place, and he's able to take them and connect them. All these pieces that might look separate and weird when they're by themselves, he's able to put the puzzle together to complete the picture. And that's what John Dalton does, as he gives us the first atomic theory. He brings back the idea that atoms do exist and that we can use them. But he needed to take a number of other people's ideas to bring them together. It wasn't something that just happened on its own. He has four things that deal with his atomic theory. The first is that each element is composed of extremely small particles called atoms. According to Dalton, these atoms cannot be broken down any further. We know that's not true. So there are some things that we know and have gained knowledge from since then. All atoms of a given element are identical to one another in mass and other properties. Partially true. But atoms of one element are different than atoms of another element, meaning oxygen atoms are not the same as a carbon atom. Sodium atoms are not the same as argon atoms. So these atoms have different properties. Again, as we go through some of these postulates or points or parts of his atomic theory, Dalton, some of these are the best that he did with what he had. And I think that's important for us to understand, is they're doing the best that they have with what they have. They didn't know about some of these other things. So when he calls ideas of atoms, they're small, extremely small, indivisible, meaning they can't be divided. They didn't know about anything else at that point. So what they knew about was what they got. And so that they're doing the best what they can with what they have. Couple other parts of his thing, in that he pulled on, stood on the backs of giants, on the shoulders of giants, so to speak, is that he took some laws, the law of conservation of mass, one of the fundamental laws in chemistry. And that was The law of conservation of mass says that matter cannot be created or destroyed in a nuclear reaction. They didn't know about nuclear reactions at the time, so they just said matter can't be created or destroyed. Okay, Antoine Lavoisier gave us that. And he had other reasons to back it up. And that's the important thing, is he didn't just say these things. He had stuff to back it up. The law of constant composition. That water is always H2O. Okay? You're not going to see it any other way. Carbon dioxide is CO2. Sodium chloride is NaCl. Certain compounds always had that same composition. He then adds on and says, well, okay, they can also lead into multiple proportions. Meaning, water might be H2O all the time, and carbon dioxide might be CO2, but can they form in more than one manner? And the answer is yes, they can. They can, actually. Because of multiple proportions, we will find that nitrogen and oxygen can form NO. It can also form NO2. And it can also form NO3. It can also form N2O. And it can also form N2O2. And it can also form N2O3. We're still dealing with just nitrogen and oxygen, but they are combining in these whole number ratios. That's the big thing. Notice I don't have any decimals or halvesies in here. Okay? None of these, it's not going to say, well, we can have a half of, how would you have a half of an oxygen or a half of a carbon atom if you can't split them? So it makes sense to them, multiple proportions. And we still hold true to this right now. We still hold true that the law of multiple proportions still is there. These are laws. We're governed by laws. We have to say there. So they're still there. Small whole number ratios. It helps us. A lot of times in the environmental sciences, we call this NOx. Because we don't know how many oxygen are present in smog or nitrogen oxides, which are a component of environmental gases. Another one is acid rain, mainly, and that's SOx, S-O-X. And it starts to sound like a Dr. Seuss book where you have Nox and SOx. Okay? Those aren't good for the environment. So Nox and SOx is bad. And as we know, some of Dalton's atomic theory wasn't quite right. We look at it now. We know that atoms can be chopped up. We know that. That's not new to us. Okay? And now that kind of gets us beyond that point of going, okay, there's other stuff going on here. Faraday and Crookes were the first to actually discover the electron. But J.J. Thomson, and I think the P isn't supposed to be there, was characterized it more thoroughly. And that's who we give a lot of credit to, is we give J.J. Thomson more credit. And Crookes and Faraday were kind of starting that idea. And we'll understand the why this becomes, why all of a sudden are we able to determine some of these subatomic particles. And when it comes to the subatomic particles for my class, we're only going to focus on the big three. And that's kind of interesting that we call it the big three when it comes to subatomic particles, because they're so small. But it's the ones that you've been taught over and over and over and over again. We're going to worry about the electron, the proton, and the neutron. There are other subatomic particles that help make up them and give them some of the properties, but I find students having a difficult time just understanding those big three and how they interact together before we even need to bring up the other ones. It's kind of like, okay, let's really understand the first step. Then if you really need to and you go on to bigger and better things, you understand what makes up those, it will be easier, I think. So that's where we kind of go with that. So J.J. Thomson discovered the electron, 1897. Electron, a lot of times we will indicate that with a E with a negative charge. Okay, it's superscripted negative. As you can see from the mass, extremely small. And it was used, again, experiments involving gases at low pressure. More specifically, it's called the cathode ray tube, is the actual item that he used, is the cathode ray tube. And they're becoming less and less prevalent in homes now. And that was where TVs, the old TVs that have a big backing of them, is like a CRT monitor. Those have a tube in them that is very similar to the tube Thomson used in his cathode ray tubes. And that experiment to kind of look at that. And in a lot of those TVs could be manipulated just as Thomson manipulated the gas, is if you put a big magnet or even just a smaller magnet near the side, the colors would distort. And that is because of some of the properties that gas has that gives us the what we see. So what does this cathode ray tube look like? Well, and we can see here in the picture, we have a electrified gas that's being shot toward and have an anode and a cathode. Now the electrified plates here allow it to focus along with these two magnets here as well. Now when we electrify these plates, they're going to start to bend a little bit. And it's the bend that they have, and we start to determine that the anode end of these beam that came this way, because they were bending towards the positive end, and they understood then that that must mean that the thing that makes up the gas, that beam of light, to be negative, because the only thing that would be attracted to a positive plate would be a negative, because they understand magnets and that opposites attract. And so by having these beams of light bending, and when those beams were electrified, it means that it was there. When they were not electrified, they would just go and run straight, just like before, just like so. But then they would electrify them, and they would bend, and therefore that bending of the cathode ray allowed us to determine that there were electrons.